Accurate, all-atom modeling of protein-ligand complexes is the foundation of modern structure-based drug design. But despite the breakthroughs from models like AlphaFold 3 and Boltz-1, generating these structures at atomic fidelity remains computationally brutal. The dominant paradigm relies on variance-exploding diffusion models, which require hundreds of iterative numerical integration steps to denoise a structure from random noise into a physically valid complex. That's acceptable if you only need a single prediction. It becomes a hard bottleneck when you want to run inference time search, virtual screening, or reward-guided optimization. Every particle in a sequential Monte Carlo sampler, every branch in a Monte Carlo tree search, multiplies that already expensive simulation cost. And since physical reward functions, things like steric clash penalties, bond geometry validators, or ligand pocket complementarity scores, are only defined on clean, fully denoised structures, you're forced to either run full rollouts or settle for noisy, uninformative guidance. So the core question becomes, can we train an all-atom Cofolding model that generates reward-optimized samples efficiently, using only a handful of neural function evaluations at inference time? The framework we're breaking down today, DECAF, or Denoiser all-atom flow map, answers that question affirmatively. It distills state-of-the-art diffusion, Cofolding models directly into a few-step flow map, while introducing a purpose-built inference framework that leverages that flow map's lookahead property for high-fidelity reward alignment. Let's walk through exactly how it works, why the technical choices matter, and what the results actually show. To understand why DECAF is necessary, we first need to look at how modern all-atom diffusion models are structured. They typically follow the EDM parameterization, which conditions a score network on a single noise level sigma. Generation happens by solving the time reversal of the forward variance exploding process, usually via an ODE or SDE solver. You sample from high noise, step down, and repeat. The problem for distillation isn't just the number of steps, it's how the noise schedule interacts with flow map objectives. EDM's noise schedule is highly nonlinear, and when you try to compute time partials for flow map consistency losses, the chain rule introduces a delta sigma/delta t term that blows up at the endpoints. This causes severe numerical instability during training. DECAF sidesteps this by reparameterizing the entire flow map directly in sigma space. Instead of working in continuous time t, they define a sigma velocity, which is simply the instantaneous derivative of the structure with respect to sigma. This eliminates the problematic time partial entirely. They then define an average sigma velocity over two noise levels rho and sigma, which becomes the displacement operator for the flow map. At optimality, this operator satisfies the tangent, Lagrange, Euler, and progressive consistency conditions that define a proper flow map. To compute the instantaneous sigma velocity from the average, they use Jacobian vector products with a stop gradient on the derivative term, which stabilizes the training dynamics. But here, where the biomolecular domain introduces a unique challenge: global rigid body symmetry. Protein-ligand complexes are invariant to C3 transformations. Rotations and translations don't change the physical structure. Standard flow map training struggles to enforce this softly during distillation. DECAF solves this by changing the prediction target. Instead of regressing the velocity directly, they parameterize the flow map as a two-time denoiser that predicts the clean endpoint XTGT. Crucially, they compute the training loss after performing in C3 rigid alignment between the prediction and the teacher's output using the Kabsch algorithm. This isn't just a regularization trick. It's mathematically necessary. If you tried to enforce this alignment with a velocity-based loss, subtracting the translation vector would break the symmetry and lose a degree of freedom, making distillation unstable. By predicting XTGT and aligning it, DECAF preserves the full C3 symmetry while drastically reducing loss variance. Now let's talk about inference. Because DECAF learns a direct mapping from any noise level to any other, it naturally defines a lookahead map. Given a noisy intermediate state x, you can compute the predicted clean endpoint 0 equals x sigma 0. This is a game changer for reward-guided generation. In diffusion models, steering decisions have to be made from noisy states, but physical rewards are only meaningful on clean structures. DECAF's lookahead lets you evaluate the reward directly in clean space, take a gradient step to optimize it, and then renoise back to a noisy state to continue sampling. They package this into DECAF Search, an inference time framework that combines a stochastic gamma sampler, Feynman-Cach steering, sequential Monte Carlo resampling, and Monte Carlo tree search. The gamma sampler injects controlled stochasticity during the renoise step, which empirically improves sample diversity without adding compute. At low compute budgets, particle-based FK steering with SMC resampling is optimal. At mid-range budgets, Monte Carlo gradient estimation on the lookahead pays off. And at higher budgets, MCTS naturally emerges as the most effective strategy. The beauty is that all of these methods benefit from the same underlying flow map lookahead, which provides a much higher fidelity reward estimate than a standard single-step denoiser. Let's look at the empirical results. The authors distilled DECAF from Boltz-1 and evaluated on the run's N, poses, and posebusters benchmarks. At strict low NFV budgets, 10 to 50 neural function evaluations, DECAF search consistently outperforms Boltz-1X across all metrics: physical validity, success rate under 2 angstrom RMSD, and local distance difference test scores. The improvements are statistically significant. More importantly, at a matched compute budget of 800 NFEs, DECAF matches Boltz-1 X's performance while using roughly 20 times less inference compute on Busters. The Pareto frontier analysis across all compute budgets shows DECAF search dominating Boltz-1 X, meaning you get better or equal performance at every single step count. They also distill the state-of-the-art Perl, Cofolding model into DECAF Perl. The result matches Perl's teacher success rate, while using 5 times fewer neural function evaluations. This isn't just a theoretical win. It unlocks practical workflows that were previously computationally prohibitive. Virtual screening, entire ligand libraries against a target becomes feasible. Synthetic data generation for training downstream scoring and affinity models scales up by an order of magnitude. And crucially, the success rate parity means you're not sacrificing structural diversity or quality, you're just getting it faster. There are some important nuances worth noting. The reward signal is inherited from Boltz-1 X, which means failure modes like non-planar sp2 bonds or overly strict Busters checks on metal coordination are baked into the optimization landscape. These aren't flaws in DECAF itself, but reflections of the underlying potential design. Additionally, the relationship between NFE budget and per-target success isn't perfectly monotonic. Different sampling strategies succeed on different complexes, which points to the value of adaptive search and potentially joint training of the flow map with task-specific rewards. The sigma-space Denoiser formulation is also architecture agnostic, suggesting this approach could extend to nucleic acids, larger assemblies, and multi-chain systems. So where does this leave us? DECAF demonstrates that you don't have to choose between atomic fidelity and computational efficiency. By reparameterizing in sigma space, enforcing soft C3 symmetry through endpoint alignment, and leveraging flow map lookaheads for clean space reward optimization, it compresses hundreds of diffusion steps into a handful of evaluations without sacrificing physical validity. As biomolecular design pipelines continue to integrate inference time search and reward guidance, methods like DECAF will move from academic curiosity to operational necessity. The code is already open, and the framework is ready to be built upon. If you're working at the intersection of generative AI and structural biology, this is a paper worth studying closely.